In this lesson, we're going to talk about vector addition and also something called the triangle inequality and the Kaushi-Schwartz inequality. So these are all related to vector operations. They're these identities, basically, that we're going to be using to verify some of our vector operations, something that you're almost always going to be taught in a linear algebra class when you start to talk about vectors. First thing is vector addition. I'm assuming that everyone here is at least exposed to the concept of that back from a physics course or something like that, but again, we will review it as we always have. So when you add vectors, you can do it one of two ways. So add vectors. The first way is graphically. And usually, this is what people are taught early on. And then after you get that out of your system, you start to use numbers to represent everything. But for now, we're just going to review real quick. So if we have two vectors, let's say I have a vector pointed this way, and I'm calling it vector A. And I have a vector this way, I'm calling that guy vector B. And I wish to add these two vectors together. All right, what you need to do is redraw the situation. So I'll put an arrow here saying that I'm moving from this representation to something else I'm going to draw. And what I'm going to do is I'm going to redraw vector A exactly as it sits, or pretty close. Maybe that's a little bit steeper, but it's attempting to draw vector A exactly as it sits. Vector B I'm going to draw as it sits, but I'm free to move it around, and I will draw it head to tail. So this is what we call vector B. So here, vector A has the same length and it's pointed in the same direction as what we have here. Vector B has the same length as what we had drawn there, and it's also pointed in the same direction. All we did was rearrange how we're drawing it so that we draw it head to tail. Head of this vector to tail of the other vector. And when you have it drawn like that, then you can directly draw the resultant, as what we call it when we add two vectors together. We go the tail of this vector up to this guy right here, and I drew a curved vector. That's never good. So do a little bit better job, hopefully. That's a little bit better. And we'll call this guy the resultant, which is basically the vector that you get when you add A plus B. Because clearly you can't just add the magnitudes of the vectors together. If I have a force here that's 10 newtons and a force here that's 15 newtons, I can't add them together and get some number just to say, well, the resultant is 25 or something, because clearly they're pointing in different directions. So some of this guy's pulling away, some of this guy's pulling away. What is the actual resultant is going to take into account the magnitude of the vectors, but it's also going to take into account the direction. So the length of A is this, the length of B is this, and the length of the resultant is clearly drawn on the board with the length of that arrow and its direction as well. All right, and so that's the power of the graphical method. It allows you to visualize what you're doing. Unfortunately, this becomes very cumbersome to solve real problems because who wants to draw arrows? And besides, this is easy because it's x, y, two components, x and y for the vectors. What if I have a vector with 3 components or more? It's very hard to draw that. So we can also add vectors. We did it graphically here. We can do it numerically. We can do it numerically. All right? So to give an example of that, let me switch back to my blue. And if I have a vector, I'll represent it here as these numbers, -1, -3, and 2 in this parentheses here, right? That's vector u. Let's say I have another vector v, which is 1, 2, and 1. See, this is a great example. This is a vector with 3 components, x, y, and z. X, y, and z. So if I wanted to do the graphical method, I would have to draw it or somehow construct it in 3 dimensions, draw the other one in 3 dimensions, and then measure the result. And it is real cumbersome in higher dimensions. So we don't really want to draw things for complicated vectors like this. So, and also keep in mind, I'm writing them as numbers with commas, but you already know by now that you can also represent it as a column matrix, -3, -1, -3, +2. And this one will be 1, 2, and 1. We can represent it as a column matrix. I'm just choosing this representation now. But to add them, we can say simply u plus v is equal to, we add the x components together. -1 plus 1 is going to give me 0. We add the y components together, giving us -1. We add the z components together, giving us 3. So you see, we just simply add everything together. And notice that I told you before that a vector is really represented in linear algebra like any other matrix. There's no real difference, remember? And I also taught you early on, how do you add matrices together? If you have matrix A and matrix B, the only way you can add them is if they're the same size, and then you add element by element, adding the corresponding elements. So if you think of this as a matrix, it has 3 elements. If you want to represent it as a column matrix, that'd be fine. That'd be a 3 by 1 matrix. You also have the same dimensionality here. You have 3 elements. So we add the first elements together, we add the second elements together, we add the third elements together. So we're being consistent. We're adding these vectors the same way that you add matrices together. And that's, again, just further proof that vectors really can be represented just like a matrix, because the same mathematical operations that we use on matrices can be applied to vectors, because they're the same thing, essentially. All right, and now what we want to do, now that we've kind of reviewed that, basically wanted to review how to add vectors for you there, is I want to talk about something called the triangle inequality. The triangle inequality. And in order to do that, you know what I'm going to do is redraw a picture that I have on the board here. We said, okay, here's vector A, and here's vector B. And the sum of those, when you add them vectorially, is you go from the tail of A to the head of B. And we call this resultant, or you could just label it A plus B. Okay? Now the triangle inequality is something you're definitely going to see in your textbook. And it's written like this. The triangle inequality says, it looks kind of scary, but it's easy to understand, I promise. A plus B, with magnitude bars around it, is less than or equal to the magnitude of A plus the magnitude of B. All right? So people look at that sometimes in a linear algebra book or whatever, and they kind of gloss over it, and they're like, yeah, I guess it's right. I guess it's true. Well, I'm going to show you why it's true. It's very, very simple to understand. What they're saying is, notice everything has a vector bar on top of it. I forgot to put the one here. What it's saying is, if you kind of cover this up, all right, just look at this. What it's saying is you have a vector A and a vector B. If you take their magnitudes and you add them together, so let's say this has a magnitude of 5 and this has a magnitude of 3. You add them up, you're going to get 8, all right? And then you compare that to if you add the vectors first and then take their magnitude, then what you're going to get is you're always going to get a smaller number on this side of the inequality. That's why it's pointing this way, than if you add the vectors, their magnitude of the vectors separately. All right, there's also a less than or equal I'll explain in a minute. The reason it's called a triangle inequality is because of what we have here. You see, length of A is represented by this arrow. Length of B is represented by this arrow. Because of the geometry, what it's saying is the length of A plus B, the length between here, that's what this term is. The length of this is always going to be smaller than if you took the length of A and then separately added it to the length of B. And you can see that from the geometry. No matter how you orient A and B, see, here's A and B now. No matter how I orient A and B, the resultant connecting those guys as a sum is always going to have a shorter arrow than if you took the length of one plus the length of the other. If you actually got a ruler out and measured this, and measured this, you would see that when you add the magnitudes here, you're always going to get a smaller number. The only time you're not going to get a smaller number is if A and B actually didn't have an angle here. If A and B were just happened to be straight, lined up straight like this, right? Then the resultant would be exactly the same as the length of A plus the length of B. That's why there's an equal sign here. So it's always going to be less than or smaller than if you individually take the magnitudes of the vectors you care about and you're adding up the magnitudes. So what you're doing is comparing numbers. So length of A plus the length of B, that's probably going to almost always be bigger than if you take the vector sum and then do the magnitude. That's what it's basically saying. All right? So that's the triangle inequality. Let me draw a little line here. Now I want to discuss something called the Kaushi-Schwartz inequality, which we'll talk about. But before I can do that, I want to talk a little bit more about the vector dot product that we have discussed so much in the past. So let's talk about the dot product again. Now, I know you know how to calculate it. We've talked about it several times, but I want to draw a picture. So let's say we have a vector here, and that's called vector B. All right, and then up above, we have vector A, like that. And in between them, because the vector A is cocked up with respect to B, there is an angle, obviously, between A and B. There always is, unless the vector A is exactly in line with the vector B, in which case the angle's 0. But at any other time, there's going to be a non-zero angle between A and B, right? Now, the dot product is something that we've talked about several times. The dot product, A dot B. We already talked about it in terms of multiplication, where you multiply the elements of the two vectors and sum the results. We've talked about that. That's one way to calculate the dot product. But another way to calculate the dot product is you say magnitude of the vector A, right, times the magnitude of the vector B times the cosine of the angle between the vectors. This is a definition that you've probably seen in a physics book, but you may not have seen these magnitudes, these double bars. That's kind of something you're going to see in a linear algebra class. Some other physics books might show it. But the way you read it is, if you're going to dot two vectors together, it's the length of A, or the magnitude of A, times the magnitude of B, times cosine of the angle. Now let me show you something to make this a little bit clearer to read over here. We can rearrange this freely, so let me circle this, because this really is the definition of the dot product, all right? But you can also write it as follows. You could say magnitude of A times cosine of theta times the magnitude of B. All I did was rearrange the order of the multiplication. I'm multiplying a number, magnitude A, times magnitude B, times cosine of an angle. So I can freely change the order of the multiplication. So I'm going to say A times cosine theta times magnitude of B. All right? And the reason I'm going to do that is because I want to show you in this drawing, what does cosine do? If you remember back from trigonometry, right? If you take the projection of this vector down to the B, to the B line there, then what's happening is this projection down here, this length from here to here, is what we call A times cosine theta. You can think of the cosine function as chopping the vector and getting the projection along the B vector. So we're looking at two vectors always when we have a dot product, and when we have A times the cosine of theta, we're looking at the component of this vector that falls along the B vector. So if I wanted to redraw it, just to make it a little bit clearer, well, let me use the same colors to make it a little bit clear. Then if I'm going to do my dot product, this is B again, right? And if I line everything up perfectly, this distance is what we call A cosine of theta, right? So it's this length from here. It's chopping it and getting that projection down. So we take A cosine theta, and it's actually magnitude of A cosine theta. So let me put that there. Magnitude of A times the cosine of theta. That's the length of this arrow, all right? And then we're multiplying by the magnitude of B. What we're doing when we calculate the dot product really is we're trying to multiply the vectors together. But really all we're interested in doing is multiplying how much of A falls in the B direction, and we're going to multiply this length of this arrow times the length of this arrow. So you can think of vector dot product as basically trying to multiply the vectors, but we only care about how much of A falls in the B direction, and that's what we multiply times B. All right, so back in physics, you learn about work. That's force dotted with distance. Whenever you're calculating work, you only care about the amount of the force that is in the direction that you push the object. Force dotted with distance. So the dot product is a way of chopping the force down if you have an angle with your force. Chopping that force down to only get the component of that force in the direction of motion. That's what we're doing here. So you can think of B might be the distance I push a shopping cart, and A might be a force vector I'm pushing on a rock. If I care about the work done, I'm going to chop it down, get the component of this force that falls in the direction of motion, and I'm going to multiply these things together. That's why the dot product is defined in this way. All right. Now, of course, I'll circle back and remind you, though, that that we have also been calculating A dot B in terms of components, right? We can say A sub x, B sub x, plus A sub y, B sub y, if it's an xy vector, right? Which is exactly the same thing as saying A sub x, A sub y, B sub x, B sub y. This is the dot product in terms of matrices. So if I know my A vector and I know my B vector, I go across and then down. So basically all I'm doing is multiplying the x components of the vectors together. I'm multiplying the y components of the vectors together. I'm adding everything together. I get one number as a result of the dot product. Notice it's completely consistent with this. I get one number as a result of this calculation. I also get a number here. This is a number. This is a number. Cosine of an angle is also a number. So I just arrive at a number for the dot product. So basically there's two ways to calculate a dot product is the bottom line. Number one, you can do it in terms of components. Number two, if I know the magnitudes of the vectors and the angle between them, I can use the other relation. They both give the same answer. Your dot product is going to give you the same thing between both of them. Now I wanted to cover this because we're going to be learning about something called the Kaushi, Schwartz inequality. And without further ado, I'll go ahead and put that on the board, and now that we've done a little review of dot product, you'll understand exactly what it is. The Cauchy-Schwarz inequality says that if you take a vector A and you dot it with a vector B, and then you take the magnitude of the result, that it's going to be always less than or equal to the magnitude of A multiplied by the magnitude of B. So it's very similar to the triangle inequality in terms of its form, and you can understand what it means by now looking at this picture that we've constructed on the board. What it's basically saying, if you look at just this side of it here, if I take the length of vector A and multiply it by the length of vector B, that's always going to be bigger than if I take the dot product and then just look at the absolute value of the result. And you can kind of see that from here. Basically, if you look at this particular case, you have an angle between A and B. All right, the length of A is this, the length of B is this. So if I take the length of A times the length of B, that's what I've got on the right-hand side. But then when I take the dot product, I'm always chopping this vector down. So the length of this chopped version in the direction of B is always going to be smaller than this. So this arrow here is always going to be smaller than the magnitude of A because I've chopped it and I'm only looking at the direction of A, or the vector A in the direction of B. So when I take the dot product like this of the two vectors, what's inside of here should always be smaller than if I multiply the magnitudes of the vectors separately because of the fact of the geometry here. The only case in which it would be equal is if the vector A already was in the direction of B. So basically theta is 0. So in that case, vector A falls exactly in the direction of B, and then I'm going to get an equal sign on both sides because A times B will be here. A dot B will be the exact same thing because the vector will already fall along B. So this is the Cauchy-Schwarz inequality there. And it's if you understand the definition of it from what I've described here from my pictures on the board, wonderful, that's what I want. Mostly you need to know how to use it, understand kind of basically where it comes from. So we're going to do a quick problem or two to verify that, to show that that's true. So what we want to do is say, let's say we have vector U, and that's going to be 1, -1, 3, and 4, right? And vector V, 2, 0, 3, 1. Again, we're not in three-dimensional space here. We have 4 numbers, so this is 4-dimensional space. This could be space-time, where the 4th dimension time, or it could be some other temperature, pressure, density, whatever else is in your space that you're considering other than position. It could be any number of things, but in any case, abstractly, your vector has 4 dimensions for each one of them. All right, so let's verify the triangle inequality. The triangle inequality we talked about before was A plus B, and take the magnitude, should always be less than or equal to the magnitude of A plus the magnitude of B. All right, so where A and B are just my 2 vectors I have. So let's go ahead and do that real quick. First of all, let's find the magnitude of each of these vectors. So the magnitude of U is the square root of this guy here. We'll have 1 squared plus -1 squared plus 3 squared plus 4 squared. And then inside here, when we add 16 plus 9 plus 1 plus 1, we're going to get the square root of 27, which is going to be 5.20. I'm just going to move it in terms of decimals so we can do a direct comparison. Now, the magnitude or the norm of V is going to be the square root of this guy here, 2 squared plus 0 squared plus 3 squared plus 1 squared. So here we have 9 plus 1 is 10 plus 4 is 14. So we'll have 14. And if you take the square root of 14, you'll get 3.74. Again, just getting decimals so that I can do a nice comparison. So what we have here is basically the right-hand side. We can calculate easily by adding these two numbers together, but let's work on the left-hand side. To get the left-hand side, first we have to add the vectors together. So now we add them u plus v. And to add vectors, we add the respective components. So we'll have 1 plus 2 gives me 3. Negative 1 plus 0 gives me negative 1. 3 plus 3 is 6. And 4 plus 1 is 5. So we have 3, negative 1, 6, and 5. So we just add those two vectors together. And now we want to find, because of the triangle inequality, we need to find the magnitude of what we got as a resultant. So we'll do the magnitude of u plus v, like that. And that's going to be the square root of the components squared. 3 squared plus negative 1 squared plus 6 squared plus 5 squared. We're just taking the square root of the squares of each of those guys added together. That'll be the square root. If you take 3 squared, this squared, this squared, this squared, add them together, you get 71, and you'll get, when you take the square root of that, 8.43. 8.43. So now we're in a position, we have all of the pieces of the triangle inequality. So the magnitude of a plus b should be 8.43. We're claiming that that should always be less than or equal to the magnitude of a, 5.20, plus the magnitude of b, 3.74. So 8.43 less than or equal to, when you add these guys together, you're going to get 8.94. So in this particular case, the triangle inequality is satisfied because when we take the magnitude of the vector sum, we get a number that's less than the individual magnitudes of the vectors added or summed together. That's what the triangle inequality is saying. It's saying when you add vectors together, when you add their magnitudes, you're always going to get a number on the right-hand side of this guy bigger or maybe equal to the vector sum. This is the graphical way of understanding it. This is the numerical way of proving that it's true. So you may be asked to do that. All right, now along the same lines, we want to, for the same vector, I'll just stay on this board. For the same vector, we want to verify the Kaushi-Schwartz inequality. Kaushi-Schwartz inequality. So for the Kaushi-Schwartz, what was that again? We'll write it down. It basically is telling us that magnitude of A dot B less than or equal is to vector A magnitude multiplied by vector B magnitude. So we should get something less than or equal to the individual magnitudes multiplied together. Now we already know what the magnitude of A is. We're using the same vectors here. That was calculated up there. We already know what the magnitude of B is. So what we need to do to get the left-hand side is find the dot product. And we know how to find the dot product because we know what the vectors are. So in order to find, in this case it's u and v, so I'll say u dot v. The u vector, don't forget, was 1, negative 1, 3, 4. I'll just rewrite it here. And we'll dot it with the v vector, 2, 0, 3, and 1. So whenever we dot these guys together, you look at the individual components. 1 times 2 is 2. And then you have negative 1 times 0, so you have 0. And then you have 3 times 3, which is 9. And then you have 4 times 1, which is 4. So u dot v, this is 9, 10, 11, 12, 13, 14, 15. So we have 15. So I have 15 there. And of course, if you take the absolute value of this, which is what we're doing here, the absolute value of a positive number is just a positive number. So to verify that it's true, the dot product of the two vectors, when you take their absolute value, is 15. And we're claiming that it should be less than or equal to the magnitude of A. Magnitude of A, which is magnitude of u, is 5.2, 0, times magnitude of B of the other vector, which is 3.74. So what we're claiming is 15 is less than or equal to, when you take 5.20 times 3.74, you get 19.45. So it's verified. The number on the left is less than the number on the right. And again, it all comes back to Kaushi-Schwartz with the definition of the dot product. When you have two vectors that are basically skewed relative to one another by an angle, Then the dot product, the definition of it is taking the A vector, chopping it, finding its component that lies along B. This component that we have chopped is always going to be smaller than the original vector A because that's the definition of what a projection is there. So the inequality, therefore, makes a little bit more sense. Whenever we take the length of this and multiply by the length of this, which is what's on the left-hand side, it should be less than taking the length of this vector times this one, because the vector A is going to be bigger than this projection. That's where that basically comes from, and we're proving that it's true there. Again, when are you going to use these? You know, we'll use them when we get into higher order vector spaces. We'll kind of use them as analogies when we go and transport ourselves into vector spaces later on down the road. But the short answer here is that in almost every linear algebra course, you're going to start studying matrices and vectors right at the beginning, and then you'll have these inequalities here, the triangle inequality, Cauchy-Schwartz inequality, where you'll be basically asked to flex your muscles in terms of understanding vector addition and dot products. And so we're mixing vectors and matrices and such, and I think I've said enough times that they basically belong in this class because vectors can be treated as a matrix, as a column matrix like that. So make sure you understand these guys. Make sure you understand how to verify some of these inequalities, very common test question. And then follow me on to the next lesson. We're going to continue learning about vectors. Eventually we're going to get into matrix, solving systems of equations with matrices and inverses and things of that nature. And we'll just kind of go down the line working everything with step-by-step examples. Learn anything at mathandscience.com.